Good morning, everybody. Thank you very much for coming to this talk today. Let me, before introducing the speaker, let me say that this presentation that will take place here today is mainly due to the Institute participation in the Horizon Europe project SCAPE, where we are developing with other partners future and, let's say, new concepts of scalable and modular electronics for electric traction. We are trying to find solutions for the power and energy management systems in electric vehicles, going from two wheels to trucks. In this framework, one of the technologies that we are using, it's a quite advanced technology, is chip embedding. Consists on putting the power devices inside the PCB stack. This has a lot of benefits, and it's also challenging. And the technology that we are using is a technology from the company, German company Schweizer. We have been collaborating with engineers from Schweizer, and in particular, Thomas Gottwald, that will present today to us their most advanced technologies. Is the CTO of the company from May. It's quite recent, but Thomas has been involved in the development of advanced technologies in Schweizer for more than 30 years. And the idea is that Thomas will present to us the different technologies they have, with main focus on the embedding technologies I have mentioned to you and that we are using in this project. Thank you very much, Thomas, and the floor is yours.
Thank you, Xavier. So actually, when I was invited to give the speech, I was happy about it because one of our customers lately told us what is new in PCB. So PCB is well known for centuries, almost centuries, but this customer mentioned there was not so much change in the last 20 years. And maybe after this presentation, hopefully I can change your minds about that. So let me jump into that by starting with some slides of our company. The first point was already mentioned correctly. Schweizer is a German, not a Swiss company, because there's also a Schweizer Electronic in Switzerland, but we are located in Germany. So I have an agenda for you. So first of all, some quick facts about our company. Then I will point out what kind of PCBs we have as of today. Then I will have a focus on power PCBs. And what Xavier already mentioned was chip embedding. This is what we are calling system in board, because we're doing the embedding in the main board, and therefore the technology is called system in board. And more than PCBs is one of our slogans, and I would like to show you today that you can do so much more with PCBs than you might even imagine. So some quick facts. Maybe I use the laser pointer at the computer. Some quick facts. We are approximately 600 employees. We have a total capacity of daily production 1,200 square meters, which is pretty much. Together with our partners, we are able to even manufacture more than 8,400 square meters per day. We are not really a startup company, so this year we're having our 175th anniversary, and our turnover is close to 140 million per year, and it will maybe this year it will be somehow stable. We have 5 locations worldwide, and we have 9 production partners. So this is the story of Schweizer Electronic. So we did not really start with PCBs. but when the company started, the people who worked there were painting animal clock faces at that time, because the watch industry settled in the Black Forest area, and because everything was already there, like printing, screen printing and etching. In 1936, the company turned into the production of aluminum and brass nameplates. So one of the most famous nameplates are the street names in the city of New York. This was one of the biggest jobs our company got, and in the old streets you can even find them. In 1958, we were the first company in Germany or in Europe overall who went into the PCB business, because also PCBs are made by screen printing and etching and solder mask printing and so on. These were the easiest PCBs at that time. Since the millennium changed, 2000 approximately, the economic pressure is very high on the PCB industry, on the European PCB industry. The pressure is coming up very hard from the Asian hemisphere. Today, you can say approximately 80% of the production is coming out of China. There are another maybe 10% from Southeast Asia, and the rest is distributed over the world. So only 3% of the worldwide production is remaining in Europe as of today. So that's one of the reasons why we had to specialize. We had to find our selling position, and we specialized on high-end PCBs, like the one displayed here, which is an inlay PCB for the automotive industry. Today, we even specialize furthermore by not doing PCB processes only, but bringing semiconductors into the PCB. And this is our major focus as of today. And also for tomorrow, we have the next generations already in mind, and we are already working on it in a serious development, and also in our innovation department on the next generations of chip embedding. So our company's positioning is that we have to add value to our company, and this added value is made of three major steps. First of all, engineering and development. So we are one of the major development partners of the German and of the European automotive industry. And if you're working closely with the development partners, you are in a good position to have the right focus and to develop the right products for the market. Today, we are specialized on radar, ADAS, and electrification of the automotive industry. So there's a lot of electrification activities, for mild hybrids to hybrids to battery electric vehicles, and everywhere you need PCBs. Today, you also use power modules and so on, but a part of these power modules might be converted to PCB technologies in the future. We have an in-house production of PCB and of chip embedding. Today, we're working on silicon MOSFET embedding, and in the future, we will increase to silicon carbide embedding and also to gallium nitride. So wide bandgap semiconductors. And the other offering that we do as our company, we have partner production. So we have a joint venture company in China that we are running with our major shareholder, WUS Technologies. They are having a 30% share at our German company, and we are running our Chinese entity with a joint venture approach. So the management is from WUS, but this company was built by us as an embedding company, so it's ESD compatible, and it's the first and only ESD compatible PCB shop, because typically for PCB manufacturing, you don't need the ESD compatibility, but if you want to go for embedding, and you have to protect the devices from electrostatics. Yeah, so we have created a partner network in the Asian hemisphere, and today we're having several partners there. So you can see our main office is in Schramberg, Germany, and we have also a sales office in Suzhou in China. We have a training office in Singapore, and our American entity is in Wilmington, US. So it is also a sales office. We have 2 production sites, one in Schramberg, one in Jintan, China, which is approximately 3 hours west from Shanghai. Yeah, and our production partners, as WUS is our major shareholder, we are also working together strongly with our partner WUS out of 2 locations. The one location is Kunshan, China. The other one is Hangzhou in China. And we have Jovi, we have FS, we have Eleconta Marek, and we have TS Technology in Poland as our production partners for different kinds of technologies. And we have sales offices and engineering partners all over the world. We are working strongly with Nagase for Japan, Vari Korea for Korea, Nisco for Israel, Trilogy for the US. We lately established a partnership with Zollner, which is a large EMS company in Germany with a turnover of more than 1 billion, and with Intron in China, who is also an EMS partner. So it's kind of a global setup. In Europe, we are having the largest PCB manufacturing company. There are companies who are making more turnover, but our company as a production site is the largest in Europe. And we established this company in China, which is about 7 times the size of our European company. So more than 7,000 square meters per day can be derived from this company. And we built now the first step, and we will increase it in the future. So what we are doing today, we are doing so-called custom PCBs, but we are totally aware that the PCBs that we are manufacturing are not really custom PCBs, because if it's a commodity, it's going to Asia. So it is custom, what we call custom. And we are focusing on the other side on chip embedding. And for chip embedding, we see several applications and several markets that we can serve. First of all, the e-mobility is right now having a big demand for power electronics and for chip embedding, because there are several advantages coming from chip embedding. In the part of renewable energy, everybody has to convert somehow the energy from the voltage level, from solar energy, from DC to AC, and so on. We are also looking into data centers, because data centers are having a lot of, they are very power hungry. And if you can increase the efficiency of a data center, you can save a lot of money and you can save a lot of energy. And this is one of the drivers. And as you can be very efficient with embedding technologies, also data centers are looking into embedding technologies as well. Telecommunication is the same, and very demanding industrial applications as well. So what market segments do we serve? As you can see, we are mainly an automotive company. So the major share is automotive that we are serving. It's more than 70% and might be even more this year. We have 20% industrial. We are increasing our aviation part and others. So the technologies that we offer, standard, as I told you, the standard that we offer is not a normal standard. It's not a commodity, but it's in our standard where we don't need any projects. We have a big bunch of high frequency applications, so radar applications from 24 gigahertz in the industrial area and for 77 gigahertz for automotive radars, for example. Power electronics plays an important role due to the automotive industry is looking into electronics, power electronics a lot. The P-square pack production, P-square pack is our trade name for the embedding technology, had already 5% of our turnover last year, and this will increase tremendously this year because we're ramping very steeply from our German entity and also from China this year. So next year, I'm expecting 10 to maybe even 20% for the embedding. Then we are pretty famous for special surfaces. NEPAC is one of them. NEPAC stands for electroless nickel, electroless palladium, and autocatalytic gold, which is a special gold surface which is feasible to do gold wire bonding. On a normal nickel gold surface, you typically do aluminum wire bonding, but on this kind of surface, you can also do gold wire bonding, which is needed for several applications that we also serve in the market. And there is a kind of a flex technology. It's not really a flex technology, it's a semi-flex technology where we do a Z-axis routing of a stiff PCB. And in the area where you do the thinning of the PCB, it's getting bendable. And so you can enter three-dimensional application spaces. So from the complexity, most of our products are so-called HDI technologies, so high density interconnect technologies. The rest of 24% is basic multilayers. We still do double-sided and even single-sided PCBs, but every time when it's a easy technology like double-sided or single-sided, there are some specialties with it. Otherwise, it would not be run at our company. So then let's talk in the next chapter about the different types of PCBs. So if you look into major electrification parts, typically you have three sections. You have a sensing part, you have a computing part, and you have an acting part. So sense, compute, act is a typical position, and you need different kind of PCBs, and you have different applications if you're sensing and if you're computing or if you're acting. The acting part typically is a power electronic part. And over the last, I would say 10 to 15 years, we developed special technologies for all of these areas. So for the sensing part, we are pretty famous for our radar boards for 24 gigahertz and 77 gigahertz. The FR4 Flex technology is a technology for cameras, for example. You might have these cameras in your car behind your back mirror. The cameras which are looking to the front are typically those FR4 Flex boards. These gold wire bonding surfaces are going into gearboxes, for example. If you have a double clutch drive, then you might have one of our PCBs under your hood. HDI technologies are used for complex computing applications. And then if it comes to acting, you typically work with power electronics. We have heavy copper PCBs, so where you have very thick copper inside with a large cross section where you can carry a lot of current. We have so-called IMS boards, insulated metal substrates. They are typically a piece of metal with an insulating layer and several layers of PCB on top. We have a so-called Combi board, which I will point out later on, an inlay board where we laminate massive inlays inside the PCB with a thickness of 2 millimeters and a certain width where you can carry more than 1000 amps if you need to. And the embedding technology is also one of the power electronic applications that we're serving. So if we look at different types of PCB, in the past, the golden rule was keep a PCB symmetric whenever it's possible. And this is still the golden rule. So if you are designing a PCB, always look that you do it symmetrically. But it was a customer request to also go to asymmetric PCBs. One of the best examples is the radar boards. So if you talk about 77 gigahertz radars, you typically have a high frequency material at the top where all the radar frequencies and the antennas are built. And you have a standard PCB at the back where you do all the computing of the signals. This is an asymmetric PCB. Typically, it tends to warp and twist, and it's kind of a challenge to keep such an asymmetric PCB still flat and not warped. And this is one of the one of our knowledges how to do that. We then developed so-called Combi boards. If you look at the schematic cross-section, you see that you have heavy copper on the one side, you have standard copper on the other side. You might have a 4-layer construction in this area of the board, and you might have a 6-layer construction on another area of this board. And this is something which was not possible in the past. What you can do with that is that you can make a power combi board where you use the heavy copper areas for carrying the high currents, and you have the normal copper areas where you can make the routing of your signals and of your electronics, of your standard electronics in one board. Typically, in the past, this was made with 2 boards, one power board, one logic board, and then you need the interconnects between these boards. If you use this technology, you only have 1 board and 1 assembly. And the new part is the embedding technology, which was derived somehow from all the previous technologies where you bring power electronic components inside the PCB. To establish these kind of technologies, you also have to take care for new materials, because new technologies typically have other properties and therefore, and also specifications. And therefore you have to always look into new materials like high frequency materials, high temperature applications. You need to have a good power dissipation from the components, from the top to the bottom or from the inside to the outside. You have to have a high voltage insulation in the future. If you look into high voltage devices, you want to handle high currents, and you also need to be reliable. So there's a failure issue called CAF, conductive anodic filament, is something which you have to look into if you're running PCBs with higher voltages and high humidity. So let's have a look into power electronics. If you have power electronics, you typically have several challenges. One of the challenges is high currents. So there's a graphic slide. It's not the newest one, but the source is from Yole, one of the companies who are doing industry analysis, and they distinguish between PCB technologies, power PCBs, and laminated bus bars. And they said the typical area for the power PCBs is here in this area, so somewhere in the hundreds of amps. But actually, if you look where we are today, we are in an area where you would not expect the PCB to be. So we have serious products where we handle more than 1,000 currents over the PCB. And this is really typically the area where you have power modules or other technologies in place. Another challenge is high temperatures. So if you look into wide bandgap semiconductors like silicon carbide, the developers want to use the higher junction temperature of the devices of up to 200 degrees. And if you want to use 200 degrees, also your material that you're using has to withstand these high temperatures, these elevated temperatures. And therefore, you have to look into new materials which are capable to handle this high temperatures. Also, high voltage insulation is one of the topics that we have to look into. And it's not only high voltage under normal conditions, it's high voltage under harsh conditions, like high humidity, like high temperatures, and so on. And you still have to maintain a good insulation on the PCB under every condition. And maybe one of the biggest challenges, you have to dissipate the power losses, which power electronics typically produce. And these have to be handled at the lowest possible thermal resistance to get most of the power out. And therefore, in the past 10 years, maybe, we developed several different technologies, which I'm going to point out. But just as an overview, if you want to handle high currents, we can offer you mainly two technologies. The one is the heavy copper technology. The other one is the inlay board. So with the heavy copper, you use standard materials, but with thicker copper platings on the inner layers. So the maximum thickness could be up to 400 microns. The cross section that you see here is 4 times 400 microns. So you have a total cross section of 1.6 millimeters of copper inside one PCB, which is quite a bit. And if this is not enough, you can also use a so-called inlay technology, where we laminate massive copper inlays inside of a PCB, where we even reduce the resistance of these conductors furthermore. We also can offer the combination of logic and power in one PCB. Therefore, we developed the so-called power Combi board. And as you can see from the cross-section, we have heavy copper parts in the inside beside logic parts in the same board. And therefore, you can do both on this board, logic and power. Another technology for logic and power is our P-square pack, or the smart P-square pack if you make it intelligent. I will point it out in detail later on. The IMS board, as explained before, is a sheet of copper with an insulating layer and 1 or 2 or maybe even 3 layers on top of it. A new technology which is evolving right now is the so-called QIT board, the quasi-inlay technology, which creates a kind of an inlay inside the PCB, but it's made with an etching process, as you might see from the cross-section. You can do this technology as an insulated technology or as a non-insulated technology. Let's have a detailed look into power. So the heavy copper boards, as you can see them here, that's a cross-section through such a board. And the strange areas that you can see here are just holes which are drilled and cross-sectioned in a certain angle. But what you see here is 4 layers of 400 microns of copper, one beside the other. And actually, if you look that there are areas which are etched, and they have to be filled in the lamination process. That shows that it's a kind of a challenge to bring this amount of resin into this construction to have a flat surface afterwards where you don't have any voids and any areas without the filling of resin. So what we typically do is that we focus on the inner layers for the heavy copper. So 105 microns, it's where we start with heavy copper layers, but it can be up to 400 microns. On the outer layers, what you see here is a 6-layer construction. On the outer layers, we typically stay with a maximum of 105 microns, because typically in the outer layers, you want also to assemble some components, and therefore you have to have a finer etching pattern, which is not possible with heavy copper. And you also want to have a good coverage of the solder mask, which is also a challenge if the copper thickness increases too much in the outside. The next heavy copper or inlay technology is since 10 years in the market. And what you can see here is kind of a switch where you have power components which have the source contact on the one side and the drain contact on the other side. And this is kind of a symmetric or a mirrored application. So here you can mount your power electronic components. They are in contact with the inlay with copper-filled microvias. So you have a very good electrical contact and you have a very good thermal contact. That means you can provide a high current on the one side, and you can have a very good heat dissipation concept with such a inlay technology. So with this cross-section of 2 millimeters in thickness and maybe 10 to 20 millimeters in width, you can provide a really good cross-section where you can run more than 1000 amps with a very low resistance to your components and back. This is used for a battery switching device. where you can handle more than 1,000 currents over one PCB. So the major electrical resistance is coming still from the components and not from the PCB. The power combi board, as shown before, here in a larger imagination, you can see here on the right side, you have heavy copper areas where you can handle the high currents for your power electronic components. And maybe you see that this area here is a BGA area where you can put your logic control unit directly on top of it. And you only have one board where you in the past had two boards, one logic board and one power board. So if you have space constraints in Z-axis or in XY dimensions, this could be a technology which is suitable for reducing the total volume of your application by doing a combination of a logic board and a power board in one PCB. You can read all the details afterwards because this presentation will be distributed also to you. So the IMS board is a copper-backed board. Typically, if you talk about IMS, most of the PCB manufacturers are using aluminum-backed IMS boards because they are cheaper. We are using copper-backed IMS boards for two reasons. The one reason is compatibility with our processes inside, and the ability to bring special surfaces onto the top, which is not so easy with an aluminum back. But there is another reason as well. The material of the copper has got several advantages. So the only disadvantage is that it has more weight. So aluminum-backed IMS boards are lighter, but the thermal conductivity of a copper backed IMS board is higher. We also have a higher Young's modulus. The CTE is lower, and this is important for a better reliability of the assembled components because it leads less stress into the solder joints if you do a soldering on the top. And also the electrical conductivity is better if you need to have a local contact. So these are running, for example, in headlights. This is one of the application, the matrix headlights. This is an application where we have 84 LEDs assembled on top of the IMS substrate. And you can create a matrix image where you can have a glare-free imaging on the street. That means you're always driving with high beam, and if you have traffic coming towards you, this is going down and taking out the traffic from the application. So now we're coming to the central technology, which is also playing an important role for the project we are running together, the so-called P-square pack technology. Maybe from the terminology, P-square pack is coming from power PCB pack. So that's the P-square because we are bringing power into the PCB. So the technology is not rocket science after all. So maybe one major difference to other competitors that are also doing embedding technologies is that we are not bringing the bare die into the PCB, but we're doing a pre-assembly. We're making a pre-assembly on a lead frame. This lead frame you see here is kind of square and having a cavity on the top side. And inside this cavity, we are assembling the bare die and making it to a so-called discrete component. It is a discrete embedding component. So it consists of a lead frame and a power device, and we call it a standard cell because today we're using the same size of cells whenever we're going to the embedding process. So this standard cell is electrically tested before it's integrated into the PCB. And what you see here on the top is a cross-section through a half-bridge construction of such an embedded device. You see one device on the left side, one device on the right side, and you see connections to the source of the component. You have the gate contact, and you also have a contact to the drain. As the lead frame is representing the drain contact, you can now take the drain contact from the lead frame, which is another advantage because by doing this, you can create very low switching loops. And as you have the interconnection from the drain to the source, you can see this here is your middle point of a half bridge. So this would be the phase contact or the phase out, the AC out for a half bridge construction. Again, you see the source contacts, the gate contacts, and the drain. What you see at the bottom is 2 levels of copper-filled blind vias. And in this construction, they are used to minimize the thermal resistance from the device through the lead frame to the outside of the PCB. And by doing this, you can create a thermal resistance as low as 0.2 kelvins per watt per cell. So when we started, we looked at miniaturization of power electronics. This was the first driver of this technology, and still it's valid because today everybody looks to get higher power density in this application. But what we also learned by making these samples and testing them is that we could create a higher efficiency in switching. So we could create lower losses, especially in the switching. Lower switching losses, and for low voltage applications, also lower conduction losses, because by replacing the bond wires that you typically have in a package by these copper-filled microvias, we could also lower the RDS on, the residual RDS on of the total device, which can be seen from the data sheet. So we could also show that we have an extremely high reliability. So typically, if a power electronic module fails in a power cycling test after 100,000 cycles, we could already show millions of cycles with the same parameters. Even if you go to higher thermal, to a higher delta T, to higher thermal differences in the switching, you can show extreme high reliability of this technology. And kind of a surprise, everybody's asking, how do you get the power out of the PCB if you have the power inside the PCB? We can do it better than a typical power module because the thermal resistance is designed to a value which is actually lower than some of the best power modules in the market. We still have some preconditions to be able to do the embedding process. First of all, we need to have the right power semiconductors with the right metallizations on the top. We need to have a copper metallization on the top contacts, and the back of the power component needs to be suitable for silver sintering or for diffusion soldering. So diffusion soldering is a special process from Infineon. Infineon is our exclusive partner for low voltage applications. For high voltage applications, we're going to a broader range of suppliers, and therefore silver sintering will play a more important role in the future. So maybe the manufacturing steps that you understand better how we do such a P-square pack. So as we are PCB guys, we're starting with PCB laminates. And this is a schematic cross section through such a inner layer material. That's how you start off. You have a so-called FR4 material, which is a glass weave with epoxy resin. And at the top and at the bottom, you have a copper foil. And in the first step, you're making a print and etch of a photolithography process with a photoresist, imaging, developing, etching, and then you create a pattern like you want to have it. And as we are making a 6-layer construction, this will be the layer 3 and this will be the layer 4. And after copper etching, you have your pattern. And here you have a special area which is released from any copper, because after the manufacturing of this inner layer, we are creating an opening in this layer with a milling process. And in this opening, we are placing our standard cell. So the standard cell and the inner layer, they are adapted from the thicknesses, so they fit together perfectly. So for the material that we're using here, we have a limited tolerance for the thickness, because this is important for the whole process. When you go to the lamination process, you are typically using so-called pre-preg layers at the top and at the bottom of this construction, and you add copper foils at the top and at the bottom. So a pre-preg is a pre-impregnated glass weave. So you have epoxy resin in a B stage, so-called B stage. So it's dried and pre-cured. And in the lamination process, you bring pressure and temperature to this construction. With the temperature, you get a lower viscosity of the resin. You fill out all the empty voids. And after the flow of the resin, you get into a curing stage where you cure the whole construction. And after this lamination process, the component is fixed inside the PCB, but it doesn't still have any contacts. So after this lamination process, you need to create openings by a laser drilling process, which are afterwards running through a electroplating process where you fill all the blind vias. What you can see here is the contact to the drain, to the gate, and to the sources of the contact. And as you do the laser drilling and plating also from the backside, you can create a very low thermal resistance by adding these copper-filled microvias on the backside of the standard cell. So the power dissipation is going here to this layer, and you still have a little bit of heat spreading. So after that, you also go through a print and etch process to create the outer pattern. And in this stage, you have a 4-layer multi-layer, and the power stage is more or less ready. You could stop here and you would have an electrical functional power stage. But what we want to achieve is an intelligent power stage. And therefore, we are adding 2 more layers at the top and at the bottom. It's 2 layers due to symmetry, because if you would only add 1 layer at the top or 1 layer at the bottom, it would start to warp. So by adding 2 layers, 1 at the top, 1 at the bottom, we're creating layer 1 and layer 6. We are again making all the holes. We are also creating through holes, but we're also drilling laser vias, and then we're doing the electroplating to make the electrical contacts to the inner layers and to the layers underneath. And then we have got such a intelligent power module, because you can now separate. On the left side, you have the power stage with all the power electronic components inside. You can have a full B6 topology or H-bridge or whatever you want. And you still have the logic control area on the right side. So you could make all of your control electronics in this area. So you can actually create a single board inverter if you want to. And what we have in mass production right now are 2 applications, and they are really using this construction. So both of them are single board inverters with a power stage in a certain area and with the logic control in another area. What you can now add is also an insulating layer underneath the power stage to have the insulation already built into the PCB. Because for high voltage, this is very interesting for our customers, because you achieve very low thermal resistances. And after doing that, you can also apply a heat sink with a thermal interface material directly under your power stage. And because there is already an insulation present in the buildup of the PCB, this thermal interface material can now be electrically conductive. That means you can have a full choice of thermal interface materials. Some of our customers are fully flat soldering their heat sink on the backside, and others are doing even silver sintering to get the lowest possible thermal resistance, because if the total thermal resistance is going to a limit, you will maximize the output current of your device. So these are the process steps in general. Most of our customers, maybe also you are interested in it, what is the value chain like, or the supply chain? So typically we have two sections, a top section and the bottom section. In the top section, first of all, we need to have a right power device. A device with a copper metallization at the top and with the right backside. And this is coming from a semiconductor manufacturer. In the past, this was a hurdle. When we started with the embedding technology, it was really hard to get components with a copper metallization at the top. But today we're talking to all the big 5 or the big 6 silicon carbide manufacturers, and they are ready more or less. Some of them are already shipping devices with copper surfaces. Others are at least working on it or having it on the roadmap for the future. Because not only for embedding you need copper metallization, but also if you want to do copper wire bonding, you need even thicker copper surfaces. As we use a lead frame, we also want to have our partners in the supply chain and taking care for the lead frame. So if we work together with an OSAT company or a semiconductor vendor, we want them to purchase their own lead frames and do the die attach in their premises. And after the die attach, doing the singulation and also the test. The test is a very important step for us in this game, because what we are doing in mass production right now are applications with 12 power semiconductors in one application. Sometimes if you have a MOSFET, all of the wafer level tests are correct, but if you switch on the current for the first time, still some components might fail. So with this test on this lead frame area, on this standard cell area, we can make sure that we have a full current test of the components. So the test coverage is the same like for a normal device which would be shipped to the customer. That means we are making sure that we are only working with good devices. You might know the terminology known good dies. We are working with known good standard cells. And if one of those devices would fail in such an application with 12 devices, you would have to throw away 11 good ones. And this is something that you do not want. So these components are shipped to us, and we are starting with the manufacturing of the P-square pack. If it's a power stage only, or if it's a smart P-square pack. And today, 100% of our products are smart P-square packs, so the intelligent version of the power stage. We are doing the manufacturing and the test. So after the manufacturing process of the P-square pack, we are also not only doing a board test, we are also doing a component test afterwards. So making sure that every component embedded inside the PCB is 100% functional. So today we are talking to our customers, so doing the sales, the supply chain management, the quality management, but in the background we have common qualification and support teams who make sure that the customer has the advice that he needs for his application, or in case that something fails in the field, we also need to have somebody who's taking care for AD reporting and so on. So today we are not having only one kind of P-square packs, but we have created kind of a portfolio. So today we are shipping already our generation 1, which is an exclusive technology together with Infineon, because we developed this technology together with them. So the standard cell was made by Infineon, and we are embedding it into the PCB. So what you see here, the generation 1 is a non-insulated version. On the back of the standard cell, you see 2 levels of copper-filled vias. That means you have the drain potential also on the backside of the PCB. For 48-volt applications, this is not a hassle, because this insulation that you need to the heatsink can be easily maintained with a thermal interface material that has to be placed anyway between the P-square pack and the heatsink to carry the excess, the power losses from the component to the heatsink. For high voltage applications like 400 and 800 volt, it is not so easy anymore. And therefore, we are working on the generation 2 right now in the series development. In that case, we're just leaving out one of these layers of copper-filled microvias, because the materials we are working with are very good insulators, but we are also working with materials who have a increased thermal conductivity. Because if you just insulate here, then you're not only electrically insulating, but you're also thermally insulating. And this is a drawback. But as a system, you can achieve the lowest possible thermal resistances. But as we did not like this increase in thermal resistance against this generation 1, we also thought about making kind of a combination of what we see in the market. If you look at power modules typically are working with ceramic substrates. And therefore, in the past, they had always have superior thermal resistances. And from their technology, we also learned that using a ceramic insulation could be useful for the embedding technology as well. And therefore, our generation 3 is using this kind of a ceramic lead frame. So it's just a ceramic substrate with heavy copper at the top and at the bottom. And as the copper thickness is more than 300 microns, you can also create a cavity at the top side, place a power semiconductor device inside the cavity, and use it like the generation 1 and generation 2 lead frames. So it's from the outline, it's more or less the same. It's a little bit thinner, but you have the ceramic insulation already built in the standard cell, which is a very nice development from our point of view. Why did we have this different kind of applications? As pointed out, in the first generation, there was no need for an insulation, because this is maintained with a thermal insulating material, but it was used so these 2 layers of copper-filled vias are used to reduce the thermal resistance from the component to the outside to a very low value. So it's in the area of 0.2 kelvins per watt. So if you have several components, this must be divided by the number of components, but per individual cell, you have 0.2 kelvins per watt. Today, this technology is running in mass production for 48-volt applications. There are cars in the streets as of today in the so-called mild hybrids with starter generators. There are different kinds of starter generators called P0 until P5. So we are working with a P0 and a P2 architecture. So the P0 architecture is just a kind of a combination of a generator and a motor. And it is placed where in former times the generator was placed. So it's the easiest replacement for going for electrification. A P2 architecture, you have the starter generator between the combustion engine and the gearbox. And this is what we're working on today. With our generation 2, we're right now in series development for the first customers. We're expecting this technology to go into market in 2026, and it's supposed to go into drive inverters for 400 and 800 volt inverters. It's also useful for DC-DC converters and onboard or offboard chargers. But as you can see, due to the insulation which is built in the P-square pack, the thermal resistance is doubled, more than doubled. It's still a good value in comparison to other technologies, but that's what we did not like about this approach. So we outperformed even power modules which are built with ceramic substrate with this technology, but for us it still was not good enough. And that was the reason why we went to the generation 3, because with the generation 3, if you use this ceramic substrate, you have a much higher thermal conductivity of the ceramic substrates in comparison to the organic material in generation 2. So depending on the kind of ceramic that you use, silicon nitride or aluminum nitride, the conductivity is 90 to 170 watts per meter Kelvin. And by using this, you can go back to a very low thermal resistance like in the non-insulated state that we use today. And this is supposed to go into applications where you need very high power density. So the total power is not decisive. So in the generation 2, we are already making inverters for up to 850 kilowatts. But if you want to have these 850 kilowatts on a very, very small space, then you have a very high power density, and then you have to minimize the thermal resistances as good as possible. And if it comes to very high power densities, we think the generation 3 will be the technology of choice. It's also going into battery electric vehicles at a voltage of 400 and 800 volts. And maybe in the future, even more than these 800 volts. So if we have a look at the roadmap with generation 1, we are already in mass production since 2022. With the generation 2, we are in series development as of today, and we think that we go into SOP in 2026. And with our generation 3, we are still in pre-development, making the first samples right now and tests with this technology. And series development might start in 2025 and mass production in 2027. So some of the results which might be of interest for you. So most of the results of this technology, we achieved in bilateral projects together with our customers, which are the tier 1s or OEMs in this world. And typically we have NDAs in place, and therefore we can only show results which are already published or which we did with partners like universities or institutes. And that's one of the reasons why we love these publicly funded projects where you have to publish because that's the chance for us to have results that we can show to the public. This was one of the projects that we did together with Virginia Tech with the Center of Power Electronics. So there's a nice publication about it. If you're interested in it, I can also provide it to you. We made such a P-square pack for double-sided cooling, which was special. So there was a heatsink at the top, and there was a heatsink at the bottom. We achieved a very low stray inductance of 0.74 nanohenries. So we are talking about picohenries today, not about nanohenries anymore. We had a very, very fast switching of 70 volts per nanosecond. And by doing this, even with this high speed of switching, we achieved an overshoot voltage of less than 50 volts. So the publication of Matthias Spieler was PCB technology comparison enabling a 900 volt silicon carbide half bridge for 800 volt applications. So today, if you look at 800 volt applications, typically 1200 volt components are used due to the overshoot voltage during switching. And with this publication, Matthias proved that you could also use 900-volt components for 800 volts. And 900-volt components have a lower RDS on than 1200-volt components. And this would be a benefit to even reduce the conduction losses, not only the switching losses. So this was a nice publication, and here you can see the switching behavior with a very fast switching of 70 volts per nanoseconds. And as you can see, the overshoot is very little, and also the ringing is very, very short in time. So as I told you, if you are interested in that, I can give you the publication. And interesting was for the double pulse testing, the double of the nominal current was used. So it was very fast, very high current, and very low overshoot voltage. So why is this important? If you can switch fast, you can increase your efficiency, because you are a shorter time in these intermediate state. So first of all, everybody in the market has now seen that IGBTs are switching slow and very high losses during switching, and silicon carbide is switching fast, and therefore the switches are less. So for example, if an IGBT in the turn-on state creates 12 millijoule, while a silicon carbide components only creates 2.8 millijoule, because it's switching such faster. And also in the turn off, there's this long tail current of an IGBT, and this leads to a very high off energy of 14 millijoules in the switching off, while a silicon carbide component has only 2.6 millijoules. So by just replacing an IGBT component by a silicon carbide component, you can save approximately 80% of your switching losses. And this is already done in the industry. So direct replacements in the same power module, and you can save a lot of energy. Tesla was the first to bring silicon carbide with this Model 3 to the automotive industry. But what happens if you would take this silicon carbide component into an embedding application? We did that together with Infineon. We made a demonstrator board and we did the measurements. And what you can see here is even though we switched not as fast as we could, so only 28 volt per nanosecond with a pretty high gate resistor, the switching energy, the switching off energy was only 0.86 millijoules. In comparison to the already pretty low switching off of a silicon carbide component, which is 2.6 millijoule, this is still only 33% of what you have in a power electronics module. That means by taking the same component that you could drive in a module into an embedding construction could save you still more than 65% of the switching losses. And this is something the automotive industry is really interested in right now, because everybody wants to increase the range of the cars, and therefore they're trying to reduce the losses wherever possible. And now I come to kind of an overview to show the competitive advantages. And what we did here was, together with a customer who is also doing modules himself, so they are having a new module they brought to the market this year. So it's a really actual module, and they did a one-to-one comparison of their technology. It was a silicon carbide frame module to our silicon carbide P-square pack in a generation 2. What they found, even though they used a ceramic substrate, a silicon nitride ceramic substrate, they had 0.7 kelvins per watt per die. If you put this as a 100% and compare it to what you can achieve in an embedding with 0.4 kelvins per watt, it's only 60%. So you can again achieve a better heat dissipation out of a generation 2 P-square pack in comparison to a frame module. If you look at the switching speed, the module is somehow limited to 20 volt per nanoseconds due to the bond wires they are having in place. Today, we know that we can switch up to 100 volt per nanosecond, so somewhere between 35 and 100 volt per nanosecond. Typically, you have to slow it down from the application if you want to run it as an inverter, because most of the motors are not compliant to this very high switching speeds. The strain inductance of this frame module was 8 nanohenry, which is a good value for a power module. The typical power module comes with up to 20 nanohenries, which are in the market as of today. And with a good design, you can achieve less than 100 nanohenry. If you're less experienced, it will be somewhere between 1 and 2 nanohenries. And maybe the most important parameter you can see here, with their frame module, they have been able to drive 3.7 amps per square millimeter installed silicon carbide surface. That was the limit they could go, and at this limit, they achieved the maximum junction temperature, while in the embedding construction, they could drive up to 5.3 amps per installed square millimeter of silicon carbide device, which is 40% more. And if you see that silicon carbide is still very expensive technology, this is one of the focuses of the automotive industry to save system costs. So if you need only 40% less for driving the same power, this is a huge cost advantage in the automotive industry. We already talked about the system, the switching losses, which are much less in the embedding topology. And therefore, our customer derived a power density in comparison to the frame module, which he placed at 100%. It is almost doubled. If you go for embedding, you can achieve 190% power density with embedding. So, as a summary, so with this technology, you can easily achieve an inverter who is able to switch more than 100 kilowatts per liter in a total power density. We have a very low switching loss due to very low strain inductances in the commutation loop. We have very little losses in operation. Conduction losses as well as switching losses can be reduced. We have a very high reliability in passive and inactive power cycling. And we can achieve the lowest thermal resistances that can be seen in the market, down to 0.2 kelvins per watt per die. If you have several beside another, this module resistance will be even lower. And we are the first company who has automotive series production running, and this out of 2 locations. So we're running the embedding technology now from our Schramberg location and from our Jintan joint venture. And therefore, we believe it is a kind of an attractive technology, not only for automotive inverters, but also for DC-DC converters and onboard chargers. And now you made it. So if there are any questions, I would be happy to answer them. Thank you.